Limiting reagent. Up till now, we've dealt with situations where we had an amount of reactant A and an excess of reactant B. What if we have a definite amount of reactant A and a definite amount of reactant B? How do we figure out how much product we can form? So here's just kind of an easy visual example. You're throwing a barbecue and you've assigned everybody a different thing to bring. One person brought burgers, another person brought buns, another person brought cheese, another person brought tomatoes. To make a burger, you need one bun, one patty, two tomatoes, and one cheese. So, is there one of these that you run out of before the other? You run out of the meat patties first, and then you have some things left over at the end. So this is what happens in a limiting reagent problem, even when we're doing reactions in the lab. If I start off with an amount of reactant A and an amount of reactant B, and I put them together, I might run out of one of them before I run out of the other, and then I have stuff left over. Now, in this barbecue example, if you have a vegetarian friend who's okay just having it, grilled cheese, then you're perfectly fine. But if everybody wanted a meat burger, then somebody's probably disappointed. All right, now let's say you're setting the table. So let's say I have asked my daughter, she's 3.5, to set the table. Sometimes she's very conscientious and she will ask what we need. Other times she just kind of grabs stuff. So a normal table setting has one fork, one knife, and one spoon. Very easy. Okay, let's say you send somebody like my 3.5-year-old to go to the drawer and get out the silverware. And the child grabs a whole bunch of random stuff. They grab 6 forks, 4 spoons, and 7 knives. Now, if we need one of each to make a complete table setting, how many table settings are possible from this mixture here? 4 settings. Okay, we need one of each. So what was our limiting item this time? The spoon. Which ones do we have in excess? Forks and knives. Okay. All right, so we can look visually at some chemical reactions. Here I've got some hydrogen gas and oxygen gas. I switched slides because my little image of myself isn't blocking the picture in this one. And so we can see that at the end, I've made some water, but I have got some of the oxygen left over. So my limiter here would have been the hydrogen because we had oxygen left over. Okay, so let's start off with an easy one with just moles. So how do we do these? What we have to do is we have to do 2 calculations. We have to calculate the amount of product formed from reactant A. Then we have to calculate the amount of product formed from reactant B. So we do the calculation twice. Then we look at it, and whichever amount of product is smaller, that's how much product we can form. Okay, because that means that that reactant ran out first. So the lesser amount of product, that's how much we can form. All right, so first, what do we have to do usually? Write a balanced equation. Okay, so I've got some iron. I'm going to heat with sulfur. I want to know how much iron 2 sulfide are produced. Now, what do we know about sulfur? Well, sulfur doesn't exist monotomically. It exists polyatomically. So this reaction looks like this. Okay, so we've got that S8. So remember, sulfur exists as S8. So now what do we have to do? We have to balance it. So we're going to put an 8 here and an 8 here. So I've got 7.5 moles of iron, 2 moles of sulfur. How many moles of iron 2 sulfide can we produce here? All right, so from the starting amount of iron. Okay, so we'll take our 7.50 moles of iron. Our balanced equation tells us that we have 8 moles of iron 2 sulfide for every 8 moles of iron. And we get 7.50 moles of iron 2 sulfide. Okay, so that's how much iron 2 sulfide we can form from our amount of iron. Now from the sulfur. Okay, we're going to start with 2 moles. Our balanced equation says we have 8 moles of the iron 2 sulfide for every 1 mole of the sulfur. And so we could potentially form 16 moles. Okay, so now the amount formed is the smaller amount. So what's smaller, 7.5 or 16? 7.5. So 7.50 moles of iron 2 sulfide are how much can be produced here. All right. So let's take a look at this one right here. We've got some solutions that contain some sodium sulfate and barium chloride. How much barium sulfate is produced? So again, we're going to have to do 2 calculations. One with our product from sodium sulfate and one with our product from barium chloride. So first off, though, we have to write out our equation. Okay, so we have our sodium sulfate. We have our barium chloride. It asks for mass of barium sulfate, so that we can surmise is our solid product. And then our other product, we've got some sodium ions and some chloride ions, so. And then solubility rules tells us that sodium chloride is soluble. And then what do we have to do? We have to balance it. Okay, so we have mass of sodium sulfate, mass of barium chloride, and we want a mass of barium sulfate. So we're going to need molar masses for all 3 of these. So I'll give these to you here. We get 142.05. Our barium chloride, 208.2. And barium sulfate, we don't need a molar mass of the sodium chloride because nowhere in the problem does it ask us for a mass of the sodium chloride. So we don't need to bother calculating that one. All right, so let's first start with the amount of product we could get from the sodium sulfate. All right, so we started off with 4.28 grams of sodium sulfate. Convert to moles. And then we can use our molar ratio in our equation. And then we can convert back to grams. Okay, and so here we get 7.03. Okay, so from our sodium sulfate, we could make 7.03 grams of barium sulfate. But before we can say definitively how much barium sulfate can be produced, we also have to check how much we could produce from that 7.16 grams of barium chloride. All right, so let's give that a shot. So we started off with 7.16. Convert to moles. That was the 208.2. Molar ratio. Again, even when it's 1-to-1, we still have to show it. Okay, so from this, we could potentially produce 8.03. All right, from the sodium sulfate, we could produce 7.03 grams, and from the barium chloride, we could produce 8.03 grams. So which one's smaller? The 7.03. So what mass of barium sulfate? 7.03 grams. Okay, so we get 7.03 grams of barium sulfate produced. So again, you have to do both calculations, and then whichever one is smaller, that's how much you can produce. Now, let's take a look at this. So we're going to have some potassium and some chlorine, and we're going to make some potassium chloride. Okay, so potassium, where chlorine's diatomic. Okay, and then we'll balance it. All right. For this one, we're going to need all our molar masses. Okay, so there's our molar masses. So first we can do from our potassium. All right, so we'll do 2 grams. Okay, all right, so from this we could potentially get 3.81 grams. Okay, before letting the video play to the next slide, you try calculating how much can be produced from the chlorine. All right, so from the chlorine, what you should get is 6.31 grams. Okay, so the potassium was 3.81. So which one's smaller, the 6.31 or the 3.81? The 3.81. Okay, so potassium's our limiting reagent. So we could potentially form 3.81 grams. Now, this is our theoretical yield. Okay, so that's how much we could form. But we did the reaction and we didn't quite form that much. We only formed 3.66. So what's our percent yield? Well, at 3.66 is our actual. The 3.81 is our theoretical. So we'll take our actual times 100, and that's going to give us a 96% yield. But that's a pretty good yield. Okay, so practice, 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 practice. In fact, the next thing I have for you is a whole bunch of ones for you to practice on your own, where all I'm going to give you are the answers.